Now, if we come back to our architecture diagram, we can see that the document ingestion pipeline has been tested properly. We verified that when a document is uploaded to Amazon S3, it triggers the Lambda document processor. That Lambda function then extracts the text, splits it into chunks, generates embeddings, and stores those embeddings in Pinecone. So the entire flow inside this highlighted section is now working successfully. This means that our system can already convert documents into searchable knowledge. In other words, the knowledge base ingestion layer of our RAG system is fully operational. Now, if we zoom out again and look at the larger architecture, we can still see that while the ingestion pipeline is working, the rest of the system still needs to be connected. The front-end application will eventually communicate through CloudFront and API gateway. From there, requests will reach our RAG chat service running on Kubernetes. That service will then perform vector search against Pinecone to retrieve relevant document chunks and generate responses using the LLM. So at this point, the data ingestion side of the system is complete, but the query and interaction layer is what we will build next. Before we move forward, there is one important architectural pattern that we need to implement, and that is the pre-signed URL upload flow. Instead of uploading documents directly through the backend API, the front end first asks the backend for a pre-signed upload URL. The backend generates this temporary URL using AWS credentials and returns it to the client. The client then uses that URL to upload the document directly to S3. This approach has several advantages. First, the backend never handles large file uploads, which keeps the API lightweight. Second, it avoids API gateway size limits. And third, it allows uploads to scale independently of the backend service. Once the file lands in S3, the rest of the pipeline continues exactly as we tested earlier. S3 triggers Lambda, the document processor generates embeddings, and the vectors are stored in Pinecone. So this pattern allows us to keep the system efficient, scalable, and cloud native. In order to create the API gateway, we first need to deploy the RAG chat service that performs the retrieval and LLM generation. And that service will run inside Kubernetes using Amazon EKS. So in this next step, we are going to take our FastAPI backend, containerize it, and deploy it to an EKS cluster. Once the service is running inside Kubernetes, it will be able to perform vector search against Pinecone and generate responses using the LLM. Later, we will expose this service through API gateway so the front end can communicate with it. Before we deploy it, let's quickly talk about why we are using Kubernetes here. The RAG chat service is a long running API service. It needs to handle incoming chat requests, perform vector retrieval, and call the LLM. Unlike the document processor, which runs asynchronously in Lambda, this service needs to remain continuously available. Kubernetes allows us to run the service inside containers, scale it horizontally, manage deployments, and monitor the application. So EKS becomes the compute layer for our RAG system. To simplify working with Docker, I have added a couple of make commands in the makefile. These commands allow us to build and run the container without typing long Docker commands each time. The first command is docker build. This command builds the Docker image for the application. The image is tagged as AI Knowledge Assistant latest. When we run this command, Docker reads the Docker file, installs the dependencies, copies the application code, and creates a runnable container image. The second command is docker run. This command starts the container locally It maps the container port to the host machine and loads environment variables from the .env file. So once the container starts, our FastAPI application becomes accessible just like before, but now it's running inside Docker. So let's take a look at the Docker file itself. This Docker file uses a multi-stage build. A multi-stage build helps keep the final container image smaller and more secure. It separates the build process into two stages. Stage 1, Builder. The first stage is called the builder stage. Here we install all the Python dependencies defined in the requirements.txt. We use a lightweight base image, Python 3.13 Slim. This keeps the container minimal. All the dependencies are installed into a dedicated directory so that only the required packages are copied into the final runtime image. This avoids including unnecessary build tools in the final container. The second stage is the runtime stage. This is the container that will actually run the application. First, we create a non-root user. Running containers as a non-root user is a recommended security practice. Then we copy the installed dependencies from the builder stage into the runtime image. After that, copy the application source code into the container. Now let's open the terminal and try executing our Docker commands. So our first command will be make docker-build. As you can see, it has successfully built my Docker image. Now let's try to run this image inside a container in our Docker. Make docker run. So the image is running. If I open the Docker desktop, you can see that I have a container naming AI Knowledge Assistant. And if I open this, you can see that the container is started and the FastAPI application inside the container is running successfully. So now that our application has been packaged as a Docker container, the next step is making that container image available to Kubernetes. Right now, the image only exists locally on my machine. But when we deploy to EKS, the Kubernetes nodes will be running on AWS infrastructure. That means they won't have access to the Docker image stored on my local computer. So we need a place where container images can be stored and pulled by the cluster. And that's where Amazon Elastic Container Registry or ECR comes in. ECR is essentially a container image registry provided by the AWS. You can think of it as something similar to Docker Hub, but tightly integrated with AWS services. Instead of pulling images from the public internet, our Kubernetes cluster will pull container images directly from ECR. This improves security, performance, and integration with AWS IAM permissions. So the first step is creating a repository in ECR. So inside the AWS console, we go to Elastic Container Registry. And we create a new repository. I'll name this repository AI Knowledge Assistant. So let's just keep everything default and click create. So our repository has been created. Next, we authenticate Docker with ECR tag the image with the repository URI and push it. Once the push is complete, the container image is stored in the registry and becomes accessible to our Kubernetes cluster. First, make sure the AWS CLI is installed on your system. You can verify this by running AWS space double hyphen version. If the command works, it means the CLI is installed. Next, configure your AWS credentials so the CLI can interact with your AWS account. So you need to run AWS space configure. Once you hit enter, you will be prompted to enter AWS access key ID, AWS secret access key, default region name, and output format. So those credentials will allow the AWS CLI to authenticate with your account. So since I have already configured my AWS CLI, I am skipping this step for me. Now Docker cannot directly authenticate with AWS IAM. So AWS provides a command that generates a temporary authentication token. So you need to run the following command: AWS space ECR space get hyphen login hyphen password space double hyphen region space AP South 1, since my region is AP South 1. So as you can see, this command generates a temporary password for Docker to access ECR. So this authentication token typically remains valid for about 12 hours. And I need to run another command: AWS ECR get login password double hyphen region AP South 1, and I need to pipe this password into the Docker login command. So this is my pipe operator: Docker space login space double hyphen username. It will be AWS space double hyphen password hyphen std in, and then the URL of our ECR registry. So we go back to our AWS console and copy the URL from here. Go back to our terminal and paste it here. As you can see, my login is succeeded. So once authenticated, Docker can now push images to ECR, pull images from ECR. So this authentication, as I said, will typically remain valid for about 12 hours. After that, you would need to run the login command again. Now let me open my make file and add another command to push the image. So it would be docker hyphen push. So here I have put two commands for tagging the image, which anyways I have already done during my build, and then pushing the image to my ECR repository. So now I'll just simply run the command make docker hyphen push. So after the push completes, the image will appear inside the ECR repository. So let me go back to my ECR console. Let me go inside the repository. Let me go to images. As you can see, I'm having the image over here. Now, one important thing to understand is when costs are incurred, ECR itself does not charge for creating repositories. Charges only start when container images are stored in the registry, images consume storage space, or data is transferred out of the registry. For most development projects, the cost is usually very small, often just a few cents per month, depending on the image size. Now that our container image is available in ECR, Kubernetes can pull it and run it as part of a deployment. So the next step is creating an EKS cluster. EKS is Amazon's managed Kubernetes service, which allows us to run containerized workloads without managing the Kubernetes control plane ourselves. However, before we proceed, it's important to understand how pricing works. For EKS, there are two main components that incur charges. The first is the EKS control plane. As soon as the cluster is created, AWS starts charging for the control plane even if there are no workloads running yet. The second cost comes from the worker nodes, which are essentially the EC2 instances that run your containers. These nodes are built just like normal EC2 instances while they are running. So even if your application is idle, the nodes will still incur compute charges. So let's just go to our Elastic Kubernetes Service console and I'll try creating a cluster. Let me give the name as AI knowledge cluster. I'll keep the Kubernetes version as the latest one. Cluster IAM role. So I don't have a role here, so I'll just simply click on create recommended role. So what it will do, it will automatically attach all these necessary policies within the role, like the block storage policy, cluster policy, load balancing policy, networking policy, and etc. So AWS has now made our life more easier by recommending the option to create the recommended roles and stuff. So I'll just quickly click create role button. So it will create the recommended role for me. For node IAM role also, I'll do the same. Create recommended role. So now I need to do the VPC configuration. So I'll just keep the VPC as the default VPC, which already has some of my subnets configured, and I'll click create. And as you can see, my EKS cluster with the name AI knowledge cluster has been created. So at this moment, AWS starts charging for the EKS control plane, which is an approximate of 10 cents per hour, even if there are no worker nodes yet. So I'll have to wait for a couple of minutes for my cluster to become active. So as you can see, the status here is showing as creating. So my cluster is active right now. So the next step for me is to create the worker nodes. So the worker nodes are essentially the EC2 instances where our containers will run. Kubernetes schedules the application pods into these nodes and they provide the compute resources for the cluster. So I'll just come to this compute tab and here you can see there are no nodes created yet. So first I'll go to my node group section. I'll add a node group. I'll give the node group name as rag workers. I'll click on create recommended role. So it will open in a new tab I'll just keep the things default and click next. Next. So I'll give a simple role name such as AI knowledge EKS node role. So why do we need this IAM role? So in Kubernetes, though, as I said, the worker nodes are actually EC2 instances, and these instances sometimes need to interact with other AWS services on our behalf. For example, they may need to pull container images from the Amazon ECR, communicate with the EKS control plane, and then manage Kubernetes networking components. So to allow this, we attach an IAM role to the worker nodes. So we keep the other things as default. And as we see that we already have some default permissions added, such as the Amazon EKS worker node policy. This allows the uh, EC2 instances to join the Kubernetes cluster and communicate with the EKS control plane. Then we have the CNI EKS CNI policy, which is for allowing Kubernetes to manage the networking inside the cluster. And then we have container registry read only. So this allows the worker nodes to pull the container images from the Amazon ECR. So we'll come below, we'll create this role. Yeah. And now we'll go back to our node group and we'll select this role. Let me just refresh it. Yeah, I'm selecting this role. Let me keep the things as default. Click next. And here we have the freedom to choose our own instance type. So I'll keep the AMI type as default, this Amazon Linux. Then in the capacity type, it should be on demand. And here, instead of t3.medium, I'll select the t3.small, which is further cheaper than the medium one. And I'll just remove this medium one from here. So this is sufficient for our FastAPI RAG backend. So for T3.small instance, the cost is roughly $0.020 per hour per instance. So we need to have two desired nodes. So if for two nodes, the cost will be around $0.04 per hour, which is just a few cents. For the storage, 20 GB storage is fine. So next, I'll come down and yeah, I'll click on next. So the node group creation is in progress. This will again take several minutes. So if you see the status here for the node group, that is rag workers, you will see that it is showing still as creating. Let's wait for a couple of minutes. So as you can see, my node group is active, and here are my two nodes with the instance type as t3.small. These are the worker nodes that I have. These are nothing but the EC2 instances. So now what we need to do, we need to make sure that we have kubectl command line installed. Kubectl is nothing but the command line tool for accessing Kubernetes clusters and pods. So we will go to our terminal editor, and here we just need to execute the command brew install kubectl. It's done. So to verify the installation, we need to execute the command kubectl version double hyphen client. So you should see something like this, client version, customized version, like that. So once kubectl is installed, we need to configure it to talk to our EKS cluster. So for that, we need to execute this command, aws space EKS space update kube config double hyphen region. It will be AP South 1 in our case, then double hyphen name AI knowledge cluster. So this updates our kubeconfig file and connects our kubectl to our cluster. So as you can see, it has added a new context. Now we need to test the connection. So for that, we need to basically run this command, kubectl get nodes. So you should see something like this, the list of the nodes which we had already seen in the console just now. So these are our EKS worker nodes. So we can verify that the connection is happening properly. Now we are ready to deploy our rack service to Kubernetes. So to deploy our rack service to Kubernetes, we need to configure few resources. So the first thing is we need to create a folder called K8s, that is Kubernetes. And these are the four YAML files we need. First is the service account. This service account is associated with an IAM role using IRSA. This allows our pods to securely access AWS services, especially the secrets manager. Another thing, in Kubernetes on AWS, the worker nodes and the application pods use different IAM roles. The node role is used by the EC2 instances running the cluster, while the application pods assume their own IAM roles using IRSA to securely access AWS services. So the role that we already have, that is the AI knowledge EKS node role, is actually the worker node role. So it is used by the EC2 instances or our EKS worker nodes, but not by the pods. So we would need another role, another IAM role, and I'll just quickly click create role, select web identity, select the identity provider as OIDC, this one. Now how did it come? So you need to create this OIDC provider in the cluster using eksctl command. So this is the command that you need to execute before. So this is the command that you need to execute first. eksctl utils associate IAM provider. Give the region, the cluster, and give the approve flag. So it will provision the OIDC provider identity. So in order to execute this command, you need to install this command line tool as well. So for that, you can just simply do brew install eksctl. So now that you have provisioned this, you need to come back to the console and you need to select this as the provider. So this will appear here after you provision the OIDC. And then you select the audience as is amazonaws.com. Click next. Search for the policy secrets manager read write. So select this, click next. So this policy is actually needed to read the secret values from AWS Secrets Manager so that your pod can read the secrets values from there. So in another tab, go to the policies section and here you can click on create policy. So we want to create a we want to create an inline policy just to give the minimal permissions. So I'll just try selecting the secrets manager from try selecting the secrets manager from the list, and I'll just open the read, get secret value, and describe secret. This these are the two permissions that I need to provide. So for this tutorial, I'll keep this as all so that any resource can access the secrets. Click next. Give the name as AI knowledge assistant ASM policy. Click create policy. So this policy has been created. Now I'll go back to my roles. So here I just need to select this, scroll down below, click next, give the role name as AI knowledge assistant role. So just create the role. So my new role has been created. Let me go inside. So I can see the permission has been attached, this AI knowledge assistant ASM policy. And if I go to trust relationships, I need to just do a minor edit of the trust policy. So let me click this button, edit trust policy. And here I need to add a line which will be this. So this line is very important. So it links the roles specifically to our Kubernetes service account, which we had created the YAML for. Now click update policy. Next, we define a config map. Config map stores non-sensitive configuration values such as environment settings or other OpenAI or AWS related configuration. These values are injected into the application containers as environment variables. For sensitive values such as the OpenAI API key or the Pinecone API key, we use the Boto3 framework into the main logic. So if I show you the config.py file, so here we are using the Boto3 library of AWS SDK, and we are basically retrieving the secrets from the secrets manager. So since we are using the AWS native secrets manager, we can do this using the Boto3 framework within the code. We do not need an external secrets.yaml file. Had it been a non-AWS secrets management software such as HashiCorp Vault and etc., we would have needed the external secrets.yaml file here to load the secrets from Vault to our container. But in this case, for this demo, for our rack project, we do not need that. Once our configuration and other settings are configured, we deploy our configuration using the deployment.yaml file. The deployment specifies the container image, resource configuration, and the environment variables. Finally, we expose our service using Kubernetes type load balancer. For this, we use the service.yaml file. This automatically provisions an AWS load balancer and exposes our FastAPI backend to external traffic. So we need to apply all these configurations at one shot. So to do that, we open the terminal and we execute the command kubectl space apply space minus f or hyphen f and then the K8s folder. So once we do this, it configures all the YAML files. So since I had already configured this earlier, so it is showing as the unchanged status, else it would have showed configured. Once this is done, the next step is to check whether the pods are running or not. So for that, we need to execute the command kubectl space get pods and enter. So you can see that one of our pod, this is running. Now the next step is to put an API gateway in front of EKS. So we will go to the API gateway service and I'll click create an API and we will use HTTP API. Click build. I'll give the name as, let's say, AI knowledge assistant API hyphen gateway. I'll click add integration. So here the type will be an HTTP URL and the URL endpoint will be my load balancer endpoint. So I'll just copy it from here. We need to add an HTTP as a prefix and then followed by the IP. Click next. Then we need to configure routes. So let's add a route. Let's say the method is post and the resource will be /chat. Integration target will be automatically this one. So this will forward request to our EKS service. Click next. So we will let the stage as default and then finally create. So our API gateway has been created. So if I go to this dashboard, the link that you can see in the left hand side, if I click it, so this is my endpoint URL. That is my API gateway URL. So this is basically the base URL of our API. So now what I can do, so instead of using the load balancer URL, I can rather do a curl on this URL. So let me just copy this URL. Let me go back to my terminal, my VS Code terminal, and so here I need to replace the URL with the API gateway's URL. Okay, so let's hit enter. Let's see what happens. Detail not found. So let's go to roots. Let's create another root and I'll name it as proxy plus. So what it will do, it will have the API gateway forward everything exactly as is. So let's create it. Okay. So let's go to integration. Let us select the integration. Let's go to manage integrations and let us edit this integration. Chat endpoint here. Let me save it. So it is working. So the API gateway is now forwarding requests to the EKS cluster and the pod running inside the container, and then it is giving us the response accordingly. In the similar way, if I just try testing the upload URL with a random file name, let's say, so it should be giving me the pre-signed URL. So let's test it. Yep, as you can see, it has given me this pre-signed URL because this is what we were supposed to get. So remember in the architecture I had mentioned that the idea is to call the upload endpoint through the API gateway to the EKS cluster, which will generate the pre-signed URL. And using this pre-signed URL from the front end, I can just simply upload my original files to the S3 bucket.